Okay, this is lesson 31, and we're just going to start out for a minute talking about symmetry. Points A and B are reflections or mirror images of one another in the line M, and point M is the point of symmetry. And when we talk about M being the point of symmetry, what we mean is that A and B are both equidistant from M. B is 5 units away, and then A is 5 units away in the other direction. And so M is the point of symmetry between them if we think of them as being reflections of one another in the line M. So we're going to talk a little bit about what it means for a graph to be symmetric about a certain line. So the graph of y equals x squared is symmetric about the y-axis because every point on one side of this axis of symmetry is paired with another point on the other side that is the same perpendicular distance from the y-axis. Okay, so like over here, you've got negative 2, 4, and over here you have positive 2, 4. So for every point on one side of the y-axis, there's another point on the other side that's on the graph exactly that many units away. So you've got negative 1, 1, and you've got positive 1, 1. There's a point here on the right side of the y-axis, and there's one just like it on the left side, the same exact distance away. That's what we mean when we say that it's symmetric about the y-axis. All right, now you notice that if you replace any x value with its opposite, you get the same y value in this graph, y equals x squared. Okay, so it doesn't matter what you put in for x. Like if you put in 1 for x, you get this point. If you put in negative 1 for x, you get a point just like it on the opposite side of the y-axis. If you put in 2, you get this point. If you put in 2 for x, if you put in the opposite, negative 2, you get a point just like it on the other side of the y-axis. So what this is saying is, so notice if we replace x with negative x, we get the same y value. If replacing x with negative x in any equation in x and y, so not just this one, y equals x squared, but any graph, if in any graph you can replace x with negative x and it doesn't change the function, then the function will be symmetric about the y-axis. So if you look at this graph, this function, if I were to replace the x in this function with negative x, and do to it exactly what I was doing to x, which is square it, notice the function doesn't change. Negative x squared is the same thing as x squared. So the function didn't change. That's how you know a function is symmetric about the y-axis if you can't see the graph. So just by looking at the equation, if you couldn't see the graph and you didn't know, well, is this graph symmetric about the y-axis? The way you can know just by looking at the equation is if you were to replace the x with negative x in the function for every time it occurs, whatever the function may happen to be, and that doesn't change the function, this function just goes right back to the way it was, then you know that that graph is actually symmetric about the y-axis. So what I'm saying is you need to be able to look at a function, just the equation, and you need to be able to tell if it's symmetric about the y-axis, and that's how you tell. By replacing the x with the opposite of x, or negative x, and doing all the things to negative x that you would do to x in that equation, that function, and then it just stays the same. That's how you know it's symmetric about the y-axis. All right, the graph of y squared equals x is symmetric about the x-axis. And you can see that from the picture. For every point down here, there's another point just like it, same distance away from the x-axis. Same thing with this point, any point on this graph, there's always one just like it on the opposite side of the x-axis, same distance away. So that's why it's symmetric about the x-axis. And this kind of situation is very similar to what we just looked at This time, notice that if you replace y with negative y, you get the same x value. So when you put in, when you see that if you have 1 for y, you get 1 for x. If you have negative 1 for y, you still get 1 for x. If you have 2 for y in this equation, the equation is y squared equals x. If you have 2 for x, you get 4, for y, you get 4 for x. If you have negative 2 for y, you still get 4 for x. So whether you put in a positive value for y or its opposite, you get the same x. That's how you know it's symmetric about the x-axis. If replacing y with negative y in any equation in x and y results in an equivalent equation, then the graph of the equation will be symmetric about the x-axis. Okay, so notice in this function here, y squared equals x, if you were to substitute negative y for y in that equation and do to it exactly what you were doing to y, which is squaring it, then it just stays the same. It's the same function. It's equivalent. So that's how you would know, just by looking at the equation, how any function is symmetric about the x-axis. You would look at the equation and you would replace all the y's that you see with a negative y and do to them exactly what you're supposed to do in that function and see if in the end the function just goes right back to the way it was. If that's true, when you replace negative y for y, then you'll know that it's symmetric about the x-axis. All right, the graph of any equation such as this circle that is symmetric about both axes, so symmetric about both axes, the x and the y-axis, will be symmetric about the origin. We say it's symmetric about the origin. If replacing x with negative x and y with negative y results in an equivalent equation, the graph of the equation will be symmetric about the origin. Okay, so in this case, you look at the equation and you replace all the x's with negative x and you replace all the y's with negative y. And if the equation stays the same, then you know it's symmetric about the origin. And what we mean by symmetric about the origin is that for every point on the graph, if you draw a line through the origin, there'll be another point exactly like it, the same distance away. And that's true for this circle, wherever you happen to be. If you draw a line through the origin, you're going to get a point same that looks just like it, the same distance away from the origin. Okay, and you can see that if you replace the x with negative x, and you replace the y with negative y, and I'm using parentheses here because if I'm replacing x with negative x and I want to make sure I'm doing the same thing to negative x that I was doing to x, I have to use the parentheses to show that I mean square the negative x. I want negative x times negative x. All right, and you can see that if you do that, negative x squared is the same as x squared, and negative y squared is the same as y squared. So the equation doesn't change, it stays the same. So therefore it is symmetric about the origin. Okay, so now we're going to talk about translations, all right? How you can change the equation of a graph in order to move the graph either left or right. Remember, translation is a slide. It's when you take a graph and slide it either left, right, up, or down. And we're going to first of all talk about how you would change the equation of a function, of a graph, so that it would move either left or right. Okay, so basically what we're doing is we're figuring out how to look at an equation and know what the graph is going to look like. And we're first of all going to talk about what you would do to the basic equation, like for say for a parabola, y equals x squared. That's just the very basic parabola equation where you have your vertex at 0, 0, so it's this red parabola here. You can see that we've listed some of the points that are on that graph, 0, 0, 1, 1, negative 1, 1, and so on. And so we're going to see what happens if you slide the graph 3 to the right. All right, let's look at this situation first. if you subtract a positive number from x, you move the graph that many units to the right, which is the opposite of what you would expect. You would think, well, if I'm going to subtract something from x, won't that move the graph to the left? Well, actually it doesn't, and you can see why if you look at the situation here with these two tables of values. All right, so with y equals x squared, you've got 0, 0. That's the vertex here. All right, but you can see now if you change the equation by subtracting 3 from the x value, instead of having x squared, now you have x minus 3 quantity squared. You've replaced x with x minus 3. What happens is now to get 0 for y, you have to put in 3 for x. 3 minus 3 would be 0 squared, and that's when you would get a 0 for your y. So now the vertex of the graph has been moved over to the right 3 places. Now 3, 0 is on the graph instead of 0, 0. And you can see, on the first graph, on the original graph, you had the point 1, 1. Well, now you have to put in 2 into the graph for x. 2 minus 3 will give you negative 1, which squared gives you 1. So to get where you used to have 1, 1, now or negative 1, 1, I'm sorry, now you have to put in 2 to get that point. And you have to put in 4. 4 minus 3 is 1. Squared gives you 1. 4, 1 for this guy. Okay, so you can see that in reality, if you subtract a positive number from the x value in the equation, you are scooting the graph to the right 3 places. All right, that's just how it happens. So it's opposite of what you expect. If you want to scoot a graph horizontally to the right, you subtract those many units from the x value in the function. All right. Likewise, if you want to move the graph to the left, you have to add something to the x value in the function. So again, looking at the red parabola, the one that's got its vertex at the origin, y equals x squared, you see where all those points are. If you change that equation to y equals x plus 2, quantity squared, now you're replacing x with x plus 2, what happens to the graph? Well, you used to have your origin at 0, 0, but now if you want y to be 0, you've got to put in negative 2 for x, because that will be negative 2 plus 2, which will give you 0 squared, gives you the 0 for y. So now the vertex is at negative 2, 0. It's been scooted over to the left by 2 units. And the same thing, like, for example, in the original graph, you've got 2, 4, and negative 2, 4. But now if you want y to be 4 in the blue, this needs to be either 2 or negative 2. And the only way that's going to happen is if x is 0. 0 plus 2 is 2, squared is 4. So now you've got 0, 4 on the graph. So where that used to be here, now it's moved over to the left 2 places. And if you want to get that other, the symmetric point that also has 4 for y, you'd have to put in negative 4 here, because negative 4 plus 2 would be negative 2, squared would be 4. So that point is moved way over here. From the original, it's got to go 2 to the left. All right, so when you add a positive number to the x value in a function, it causes the graph to move to the left 2 places. So this is helping you, because when you see an equation that has this form and you look at the x value and see, has something been added to it, has it been subtracted from it, from the basic equation of a parabola, you'll know where that parabola is located, where its vertex is going to be located. All right. Now, so for example, if you want, this works for any kind of equation, not just a parabola. So if you want to graph the equation y equals absolute value of x, then that looks like a v, remember, right here. Write the equation of this graph translated 4 units to the right. Okay, well, if you're going to translate it 4 units to the right, you have to subtract 4 from the x value in the function. So you're going to replace the x in the function with x minus 4. So the new equation will be y equals absolute value of x minus 4. And that will give you this graph. the one that has the little bottom of the V at 4, 0. So moving the graph to the right involves subtracting from the x value in the equation. All right, to translate a function vertically, we add or subtract something from the y value. It's the same rule. If you add a positive number to y, the graph moves down, not up. If you subtract a positive number from y, the graph moves up. All right, it's backwards again, but the problem is it's not going to look that way once you put the equation back the way it's supposed to look with y on one side and everything else on the other side. Because we always write functions as y equals something. If you write y minus 3 equals x squared, you're going to rewrite that as y equals x squared plus 3. So you really did subtract 3 from y. But once you move it to the other side, it looks like you added. So let me just go through this a little more carefully, just so you don't get confused by this. All right, but the rule, like I said, is the same as the rule for x. You add something to y to make the graph go down. You subtract something from y to make the graph go up. But it ends up looking like you're adding when you're subtracting. So I'll show you why. Suppose you've got the basic parabola function, y equals x squared, the red parabola where its vertex is at 0, 0. And then you add 3 to the y. Well, if you add 3 to the y, then when you used to have 0, 0, now if you have 0 for x, you end up getting -3 for y, because if you want this to be 0, you're going to have -3 for y. So the new vertex is at 0, -3 down here, the blue parabola. So subtracting or adding 3 to the y value causes the graph to move down. But when you rewrite the function, you write it as y equals x squared minus 3, because that's the proper way to write it, with y by itself. So in the end, it looks like you're actually subtracting 3 from the right side of the function, and that will move the graph down 3. So at some point, you're going to get used to noticing that really to move a graph vertically down, you are subtracting a number from the right side of the equation, the right side of the function. But you're actually adding 3 to the y value. And similarly, with moving the function up, if you subtract a value from y, so your original function, the red function, has 0, 0. When you subtract 4 from the y value of that function, the vertex becomes 0, 4, because now to get, if you put in 0 for x here, that means that y has to be 4 to make that happen. 4 minus 4 is 0. So now the new vertex of the function is at 0, 4. So it's been moved up. The function has moved up 4 units. But when you rewrite it, so you are subtracting from y to make the function move up. But when you move that 4 over to the right side of the equation, you're actually adding 4 to the right side, and that will move the graph up. So I hope that you get the hang of what's happening there. You really are subtracting from y to move the graph up, but in the end, it looks like you're adding 4 to the right side of the equation. And if you want to remember it that way, you can. But just remember, you're not adding 4 to y. You're adding 4 to the right side of the equation. You're actually subtracting 4 from y to make the graph go up. And you're adding something to y to make the graph go down. But, yeah, I hope that makes sense. I hope I didn't cause you confusion. Anyway, so the graph, if you have the equation y equals the absolute value of x, and you want to write the equation of the graph translated 3 units up, and let's change that to a 4, because that picture is actually, well, I don't, hopefully I didn't do that wrong, but anyway, that graph is 4 units up, not 3 units up. If you want to rewrite this equation so that it moves the graph up 4 units, you add 4 to y to make it go up. You subtract 4 from y to make it go up. Get rid of that. right, so you subtract 4 from y to make the graph go up. Rewrite it exactly the way it was before, this, except now instead of y, you're going to put y minus 4. That makes the graph go up. But now, when you write it, the final equation you're going to write, you're going to move that 4 over to the right side of the equation, and it will look like this. So this is the equation of that graph. That moves the graph up 4 units. And actually, well, yeah, just don't worry about that. All right, moving on. Okay, reflections. Okay, so that's how translations work. Add something to x, the graph goes left. Subtract a positive number from x, the graph goes right. Add a positive number to y, and the graph goes down. Subtract a positive number from y, the graph goes up. Now, reflections. In any function, if we leave y unchanged and replace all the x's with negative x, the new function will be a reflection of the old function in the y-axis. All right? So you have this parabola here that has its vertex at 0, -4, and it looks like this on the left side. If you go through and replace all the x's in that equation with negative x, the new equation will look just like the other one. The new graph will look just like the other one, except it will be reflected across the y-axis to the other side, and it'll be the exact same distance from the y-axis that the other one was. So if you want to reflect a graph across the y-axis, you replace all the x's in the equation with negative x. And so this final equation would just be y equals x squared minus 8x plus 16. Okay, if you want to reflect a graph across the x-axis, then you will leave the x unchanged and replace all the y's with negative y. Okay, so in this situation, you've got this graph here, which is opening upward. If you want to reflect it down across the x-axis, then you would go and change y to negative y, which means that when you finally write the final equation, you're going to multiply both sides by -1 so that you'll have y equals something, because we always write a function as y equals something. I mean, most of the time we do. And in the end, that one down here will be y equals negative x squared minus 8x minus 16. So, to flip a graph across the y-axis, replace all the x's with negative x. To flip a graph across the x-axis, place all the y's with negative y. All right, so let's see what we can do here with this information. So the graph of the equation y equals square root of x is shown here, so that's right here. The graph on the right is the same graph reflected in the y-axis. And yeah, so we're just reflecting it in the y-axis. So whenever we want to reflect a graph in the y-axis, we exchange x for negative x. So wherever we see an x, we're going to put negative x. And so when we do that, we're going to have y equals the square root of negative x. That would be this function here. And you can see that, of course, for this function, all the x values have to be negative, because if they weren't, we'd get an imaginary number. So x has to be things like -1, -2, because you're going to take the opposite of it. So when you have, say, -4 for x in this function, if you fill in some numbers, so x, y, if x was -4 and you put that into this function here, you're going to get the opposite of -4, square root of the opposite of -4, which will be the square root of 4, which will be 2. So you can see that the point -4, 2 is going to be on this graph if you just stretch it out a little more. Okay, so flipping a graph across the y-axis just means change x to negative x everywhere you see it in the equation. All right, the graph of the equation y equals square root of x is shown on the left below. The graph on the right is the same graph reflected in the x-axis and translated 3 units to the left. Write the equation of the graph on the right. Okay, so starting out with this graph, y equals square root of x, we're going to flip it over the x-axis and scoot it to the left 3 places. So if we're going to scoot it to the left 3 places, we have to add 3 to x. So here's the function. It was the square root of x. Now we're going to not put x in there. We're going to put x plus 3. Because if I want to scoot it to the left, I have to add 3 to my x. And then we're going to, since we want to flip it over the x-axis, we replace y with negative y. So this is the process. We added 3 to x to get it to move to the left 3 places. And we switch the sign on the y to make it flip over the x-axis. And now when we write it, our final answer, we want to have a positive y, so we'll multiply both sides of the equation by negative 1 to get y equals negative square root of x plus 3. All right, so this would be the equation of that function, and you can see if you just plug in a couple of points there for x and y that this really is true. If you put in negative 3 for x, negative 3 plus 3 is 0, so negative square root of 0 is just 0. If you put in, say, 1 for x, then 1 plus 3 would be 4. Square root of 4 would be 2, so it would be negative 2. So 1, negative 2 is on that graph. So you can see that this actually does represent what's happening here. All right, so write the equation of the graph that has the same shape as y equals 1 over x, but is translated 3 units to the left and 4 units down. All right, so you've got y equals 1 over x. You want to change it so that it's going to go 3 units to the left. If you want it to move 3 units to the left, you have to replace x with x plus 3. So I'm replacing x with x plus 3. That moves it 3 units to the left. If I want it to go 4 units down, I have to add 4 units to my y. So this is what will happen, and then you rewrite the equation y equals, so you subtract 4 from both sides. So the new equation is 1 over x plus 3 minus 4. So that would be the final answer. That would be the final equation of that graph.